Welcome to another video. We're going to talk about the theorem which tells us that given any finite integral domain R is also a field. Now, the proof is simple, but very nice, and demonstrates a sort of interesting algebraic way of thinking about things. Now, let A be some element of the underlying set of the integral domain. Essentially, we want to prove that R is also it is a field, and as such, we want to actually prove that every element of the integral domain has an inverse, has its own inverse. Now, we choose some element A, and we want to show that it does have an inverse contained in the underlying set of the integral domain. We construct a new map, FA, which maps the underlying set of the integral domain onto itself, so it's an automorphism, such that it maps x onto A times x, right, where x is some element from the integral domain, obviously. Now, now we know that this map is injective, so we know that FA is injective. How do we know this? Well, we know it from the elementary properties of rings, right? That so long as A is non-negative, which we also assume and I haven't written down, then it's gonna happen that if we took some two distinct elements of the underlying set, we applied the dot operation on them with some other number, well, with some other element of the underlying set, and we got the same result. It cannot happen in an integral domain. So we know that FA is injective, and because we have an injective map, so because we have an injective map on, or rather, between two finite sets of the same cardinality, FA is bijective. Right, but this means that there must exist, since it's bijective, F inverse is well defined for all elements from the image, that being from the underlying set of the integral domain. Thus, the inverse element of A is equal to the inverse of FA of 1. So what x we would need so that A times x is 1. That's A inverse by definition. And this concludes this rather short but interesting proof.